So yesterday I asked you to highlight in your reading a few important things, including the definition of internal energy, 2 causes of internal energy, external energy, the definition, 3 things that affect how much external energy we have, then the definition of insolation. So let's hit that reading. What is the definition of internal energy?
I got you.
No, Cadence got me, because she highlighted it.
The energy that comes from inside.
Energy that comes from inside the earth. I would like to now put that in here in our brand new packet. So again, energy that comes from inside the earth. Straight from the reading.
You're late.
Guys, focus. Then I want 2 causes of internal energy. Again, where did this come from? Straight from the reading. So same thing with this. So Jeff, you have 1 cause that you highlighted yesterday. We're on the internal still, so up at the top paragraph. So internal energy refers to the energy that comes from inside the earth. I want to know where it came from. Some energy is left over from the formation of the planet. As long as we're there, Sarah, tell me the second cause of internal energy.
Radioactive decay.
Radioactive decay. So I think we can shorten up that first one to heat left over. Oh, I guess it's not too much shorter. So the first one that Jeff told us is heat left over from the formation of the earth. And then Sarah told us the second one, which is radioactive decay. Does radioactive decay sound familiar at all? It's the half-life stuff we just did. I did fail to kind of elaborate on that last chapter. So not only does uranium go through radioactive decay and that half-life stuff and turn into lead, it also gives off heat while it does that. So some of the internal energy is coming from that radioactive decay we talked about last chapter. Destiny, did you find external energy? What'd you got? That's not the where I just want what is external energy. The sunlight is Earth's primary source of external energy. So again, I'll kind of sum that up. I have external energy as solar energy. Right, you did kind of have to put 2 and 2 together. So the energy from the sun is our external energy. So solar energy, if you do not know what solar energy is, I'm going to just say from the sun. If you are fully aware that solar energy is energy from the sun, you don't need to put that second part. Okay, it's kind of far away. Now this next part, I wanted 3 things that affect how much energy we receive from the sun. I'm not gonna go around the room, but I would like somebody who hasn't spoken yet, if you would volunteer. I'd appreciate that, but this one seemed to be putting some people on the spot. Well, actually, Cassidy, do you have the first one? Things that affect how much external energy we have? That's absolutely one of them. So that's down here. Another factor that affects the amount of insolation is the length of time the sun is visible in the sky, or that just means the number of hours between sunrise and sunset. Or to summarize this is called duration of insolation. Do you guys know what the word duration means? Time period, right? Like, so what is the duration of this class? It's 43 minutes. It goes from whatever time. It starts in 10:39 to 11:21. That's the duration of this class. So the duration of daylight just means when does the sun rise, when does the sun set, and how many hours is that? So on this side, we're going to go with the official definition. So duration. Duration of insolation, which is just the number of daylight hours. You guys do know that that's not just a hashtag, it stands for number, right? Just checking. Yeah, hashtag of daylight hours. So Cassidy found that one. Did anybody else find another one? You got another one, Keith? Yep, so that is called, so in the reading, that's down here. So it says the amount of insolation that reaches Earth's surface is controlled by how much the atmosphere absorbs every day. For example, on a cloudy day, less insolation is received by Earth than on a clear day. So how can we sum that up in a line or two? I say the amount of solar energy absorbed by the, actually, let's call it atmosphere transparency. Which just means how much energy can get through clouds. So today we're getting way more solar energy than we had yesterday. You can remember yesterday it was 100% cloudy when you looked out there. Today it's 0% cloudy. You don't see any, right, Carter? I don't see any.
Zero cloudy.
You can see more of the sky.
So blue.
Yeah, there's some clouds.
Just a few. Pretty nice out though. All right, anybody get the very last thing that changes how much, Sarah?
Electromagnetic waves.
No, that does not. It does not affect how much energy we get from the sun.
The angle between Earth's surface and the incoming rays of the sun.
Yes, that is,
Third
yeah,
paragraph.
right here. The angle between the Earth's surface and the incoming rays of sunlight, which is called the angle of insolation, affects how much solar energy reaches Earth. If the sun is directly overhead, we're getting a lot of energy. If it's low in the sky, we're not getting a lot of energy. So again, in your notes, this is called the angle of insolation. And it's just how high sun is in the sky officially, but I ran out of space. So the angle of insolation is just how high the sun is in the sky. Now, I think I probably should change this around and put insolation first, but we use insolation in each, we didn't use it in the second one, but what is insolation? Again, this was something you were supposed to highlight. Kat, did you highlight the definition of insolation? We skipped you earlier. Yeah, we already did the what it's controlled by, but I'm just looking for the definition. Okay, you got it, Caitlin. Yep, right here. Where the word solar energy. Oh, there we go. Solar energy that reaches Earth is known as insolation, or you could say this could be thought of as a shortened form of the phrase incoming solar radiation right there. I think you should highlight both of those. And insolation, we're going to go with the first part that we highlighted, solar energy that reaches Earth. And then I have a little bit of space here between the next box. I am going to do that second part. It stands for incoming solar radiation. Did anybody just think I was saying the word insolation wrong? Yeah, it's insolation. And where does that come from? Comes from the word in, or the in from incoming, the sol from solar, and the ation from radiation. So they really just made up a word for incoming solar radiation. Different than insulation, you know, the pink stuff you put in your attic or wherever, or if you get an insulated water bottle, not that. No, that's a U. No, this is an O. That's a U. We're gonna do this compare and contrast tomorrow. Okay? So that we're just re-hitting the same information again tomorrow. See if it helps you remember it. So for now, we're done with page 3, and we're gonna flip over to page 4, and here's where you're gonna need your reference table. So if you don't already have that out, grab it.
There you go.
Perfect. Okay, so we're on page 4, and everything else we're gonna do today is just making sure you're comfortable using the reference table. And I'm gonna actually kind of point out, guys, you've learned more than 3/4 of the reference table already. So what I want you to do is try and find the page all on your own that will have the selected properties of the Earth's atmosphere. So flip through every single one of you, just grab your reference table. Don't tell anybody, it's a secret. So grab your reference tables, flip through until you find a reference table that has to do with the atmosphere. Hint, we haven't done it yet. So it's one you haven't seen. So everybody just start flipping through. It's a secret and you're wrong. Okay, so you did find word, okay, I'll give you that. So I'm just gonna flip through, I'm asking you guys to do this too, but I wanna point out, if we're looking for, just like Carter just did, anything having to do with the atmosphere, anything on page 1 about the atmosphere? There is.
That's
Okay,
chemical compound.
the average chemical composition of the Earth's atmosphere. By the way, your homework has something to do with this as well, because this does tell you what some of the atmosphere is made out of. So we have the crust, which you guys should remember is the solid Earth we're standing on. Hydrosphere, who remembers what that is?
Water.
That's the water label, or layer, sorry, water layer. And then the troposphere is a layer of the atmosphere. It's the one where our heads are in. We're gonna learn more about those layers today. So there is this page on the front page. I like to remind you of this because this is the easiest chart to read, but it's the one almost everybody forgets about because it's that easy. The only thing they're really ever going to do is ask you, well, how much oxygen's in the atmosphere, something like that. Or they might say, is there more oxygen in the atmosphere or the hydrosphere? Super easy to read, but you forget about it and you think you're supposed to know those numbers off the top of your head. You do not need to know any of this off the top of your head. Okay, keep turning your pages. You're like, no atmosphere on the map, neither map. These should look familiar. These are rocks, no atmosphere. Pages 8 and 9, yes, it did kind of talk about oxygen that entered the atmosphere over here, but not what we're looking for. Some of you might have thought that you should look here where it talks about the different layers of Earth. It's not it, but it is a place that I would not have blamed you for going because that's the one where we talk about the layer. And I also did say we haven't done it, so you knew it wasn't that one. Moving on, we've got earthquakes. Page 12, if you read through, there is nothing about atmosphere there. Now, Carter did find something about atmosphere somewhere here.
One atmosphere on the right hand side.
Right there, okay, so one atmosphere, so again, we do have the word, we will do both of these pages within the next couple of weeks, so these are the first two out of all of these that you haven't touched yet, so we will be doing these in the next couple of weeks. But here's where I want you, top of page 14, that was last year's reference table, so I want this year's, same one, just not written on yet. So here's where we're going to be. You may have already also noticed we have not talked about the other two diagrams on this page or anything here. By the end of this chapter, we will have done everything except for this last page. Or, well, page 15, because we have already done page 16, which was minerals. So you guys have pretty much learned, or you will by the end of this chapter, learn 15 out of the 16 reference table pages. And if you remember back to the beginning of the school year, I told you that if you can read the reference table, you will pass the region if you read them and use it correctly. So you guys are on your way to being able to pass the regions, no problem.
Can I pass it right now?
Maybe. I think after this chapter, you probably could pass it as long as you knew how to read every single reference table. Anyway, we'll get back to that another time. So we want to use the top of page 14. In fact, in your packet, I'd like you to label that. So it says selected properties of the Earth's atmosphere for the following questions refer to ESRT page 14. I'm going to pull this up on the PowerPoint just so it's easier to read. So this is the same reference table you have in your own reference tables. There we go. So you have this same thing in your reference table, and at first, I do think it's kind of overwhelming. It's a lot going on. But what is it? Just three different what? What is it? Line what? Line graph. So this looks super overwhelming, but it's really just three different line graphs. We'll break it apart bit by bit. Yes, there are spheres listed on here, but let's start from the beginning. Three different line graphs. We have a graph for temperature. We have a graph for pressure. And a water vapor concentration graph. Three separate graphs having to do with three very different things. All three graphs have their own x-axis, but they all share a y-axis. So that's where I want to start. Take a look at the y-axis. It's altitude. Do you guys know what altitude means?
Altitude of Polaris.
Okay, so what does that mean?
Latitude.
No. The altitude of Polaris does equal your latitude, which I like that you remember, but that's not what we're talking about here. What is altitude? It's how high up in the air you are. So like if you're in an airplane, the pilot will come on at one point and say, we're at a cruising altitude of blah, blah, blah miles above the Earth's surface. And so that just means how high you are above the Earth. In fact, let's label that on your reference table in case you forgot. So really all I want to do is altitude is how high above the ground. Speaking of ground, where is the ground on this reference table? 0. It says sea level. So sea level is officially where the sea meets the land. So like at a beach, you are 0 feet above the sea level when you're standing at a beach on the ocean. most places are not 0 feet or 0 anything above sea level. We could look up, we could Google it, do a quick Google search, but we're gonna do that at the end. But we are not quite at sea level here, not super important though. So we have the ground at the bottom of this at 0 miles above sea level, and then it just gets higher. One thing I do want to point out that's weird that people will mess up is that they give you both kilometers and miles here. So the kilometers is the scale on the left, miles is the scale on the right part. And yeah, they're going to try to mess with you. Sometimes they give you miles above sea level. In the next question, they might ask you or give you kilometers above sea level. And I can guarantee you if it's multiple choice, they will have the opposite right answer there. But so if the answer was 50 miles, one of the answers will say 80 miles. So see how they line up? They're just trying to mess with you. So always make sure you read all the words, including labels. Other than that, it's pretty easy to read. The scales are a little bit different. How much are the lines going up by in the kilometer side? So yes, they label every 40, but what are the unlabeled lines? Hopefully you can see it's 10. If you did not see very easily that it was 10, all you got to do is just pick some numbers that are easy to count by. Always start with 1. Are they counting by 1? 1, 2, 3, 4. No. Counting by 5, 5, 10, 15, 20. No. 10, 10, 20, 30, 40. So just try stuff. I promise you it will never be something difficult to count by. So they never count by 3s. They'll never count by 4s. Something easy. So let's label that. Make sure you're on the kilometer side. 10, 20, 30, and then the 40s there. If you want to go up the whole way and label it, you can. I'm just going to do that first set to get you in the mindset that that side's going up by 10. Is the kilometer, or I'm sorry, is the mile side also going up by 10?
No.
5.
Right, in this case, hopefully again, you tried something, tried 1, 2, 3, 4, 5, didn't fit. Tried 2s maybe, but 5s fit perfect. Again, I want to label one set of those. So this side is 5, 10, 15, 20, 25 is labeled. So that's the or that's the y-axis, the same for all 3 graphs. So no matter what, as you get higher up on this graph, it just means you're getting higher in the atmosphere. You can almost picture it as like flying in an airplane and going up. In fact, I do want to show you one picture that shows what this would look like. So here is a picture of what it would look like if you were in an airplane flying above Earth's surface, or even going up higher than that. So here you can see we've got the ground listed here. There's hot air balloons. I don't think hot air balloons and planes actually can be the same height, but maybe they can. I don't think so. Here's a weather balloon. Here's some satellites. So you can kind of get an idea of what it would look like. You're just traveling in an airplane or a balloon, getting higher and higher and higher in the atmosphere. Now back to the graph. Temperature graph. You notice this line is zigzagging back and forth. What does that zigzag mean? Let's start at the beginning. When you're standing on the ground here, what's the temperature according to this graph? 15 degrees Celsius, right there. The black line for the line graph lines up with the 15. But as we take an airplane up into the air and hit this dotted line, what happened to the temperature during that time? Did the temperature go up or go down? It did decrease. So you should notice, yes, we got higher in the atmosphere. So if this was you, you'd be walking higher into the atmosphere. But what's happening here to your temperature? You're going from 15 here to right here. Notice they put those nice dotted lines there. Those dotted lines tell you the exact temperature right there. So -55, be careful of that, because that is another way they'll mess with you, is they'll leave those negatives off, and you'll get it wrong because you just saw the number. Now, notice, that was called the troposphere. That's the layer on our reference table on the front page. That's the one we're living in right now. Your head is in the troposphere. Okay, it changes. So that's one of the layers. And then it starts into another sphere. There are 4 spheres. Each sphere is kind of marked off by those dotted lines, the horizontal dotted lines, and those are called pauses. What happens at every single pause? The temperature changes, or the trend for the temperature changes. In the troposphere, we go from 15 to -55, so we get colder. What happens as soon as you hit that dotted line? What starts to happen with the temperature? Starting to get warmer. Let's label that. Here, it's colder. Here, it's getting warmer. Now, does it get very warm?
No.
Like, are we sitting in a sauna when you're in the stratosphere? No, what's the highest temperature it could be in the stratosphere?
Let me check.
Check your reference table. Everybody check your reference table. What's the hottest it could be in the
0.
stratosphere?
0.
So notice, which way do I have to go? Do I go down or over to figure out the temperature?
Down.
Down. So here the temperature is -55. As we get higher up into the stratosphere, right here is the hottest it can be. Follow the dotted line. The hottest it could be is 0. Hey, do you guys know what happens at 0 degrees Celsius? Okay, if you did not know that off the top of your head, maybe label it. Freezing point. 0 Celsius is the freezing point. So the stratosphere never gets warmer than freezing. We hit the stratopause. Again, do you notice how close those words are to each other? Do you think they're ever going to try and trick you and put the word stratopause instead of stratosphere? 100%. So what do you need to do? Pay attention, read carefully. Number 1 rule of earth science, read all the words. So again, you hit stratopause, what happens to the temperature now? It's -90. We start off at 0, we end up at -90. Yes, we're getting higher, but please don't get confused getting higher in the atmosphere to getting warmer. Okay, it is here we're getting colder. And we're talking -90 degrees Celsius. That's freaking cold, guys.
That's freaking cold.
It is freaking cold. Finally, we hit the mesopause. What happens to the temperature? It increases a lot. I also want to point out a trick that they are doing to you. Read this word phrase under the word thermosphere.
600.
Extend to 600 kilometers. Our graph ends at 140. But what they're saying by adding this is this line continues the way it's going all the way to 600, which is a little more than 2 more graphs worth. So it keeps going. It just keeps getting hotter and hotter and hotter in the thermosphere. Again, be careful. Do not confuse the words troposphere, tropopause, and thermosphere. If you just read those quickly, you wouldn't be paying attention. You might just see the T and assume it means the wrong thing.
Well, the number 1 rule of earth science is.
Right. As long as you follow along with the number 1 rule of earth science, you'll be good. That's the temperature graph. So why do you think they designated the spheres where they did? Did they just randomly decide to put the troposphere here, the thermosphere there, the stratosphere, and the mesosphere?
No.
No, it's not random. What decided where one started and the other stopped?
What if
the temperature line. So where it goes, when it switches, that's when they decided to make a new sphere. So that's temperature. Let's talk about pressure. So, what? Pressure goes from 0 to 1 atmosphere. ATM stands for atmosphere. 1 atmosphere. Where do you think they got that unit of measurement from?
The ground up.
The ground up, here's the atmosphere. When you're standing down here, you have the entire atmosphere on top of you. So I know you don't feel like air weighs that much, but it weighs something. And when you have this much, the weight of the atmosphere is pushing down on you. 1 atmosphere is equivalent to how much air is in the entire atmosphere. So when you go up in the atmosphere, you have more or less atmosphere to push down on you. Yeah, if you were here, you don't have very much atmosphere on top of you, so there's less pressure pushing down on you. So as you should notice, on the ground, the pressure is 1. But what happens to the pressure when you go up? It decreases, it gets closer to 0. Please don't get that confused. When you go up in the atmosphere, the pressure decreases. Now, water vapor, why do you think this graph is so little? Why didn't they put anything up here?
Let's go up there.
Because it doesn't go up there. So where's the water?
Okay, where it is.
Where the graph is, where's the most water? It looks like it's somewhere here, but what I'm getting at is the troposphere. Most of the water's in the troposphere, a little bit goes to the stratosphere. Guys, there's a lot of water here. Like outside right now, there's some water.
I don't see water.
Snow.
No, that's water. Rain, that's water. Humidity, that's water. Guys, for weather, what do you think you need a lot of to have weather?
Water.
Water.
H2O.
When you're in a plane, for those of you who've been in a plane, when you look out the window and you look down when you're flying, what do you typically see when you look down?
Earth.
Yes, Earth, but most of the time there's clouds as well. Airplanes go above the clouds. Now, if you've ever paid attention, once you're in that airplane, looking down at the clouds, have you ever looked up
No,
out the
Yeah.
window?
not possible.
Well, you can get a little bit of a view. There's not many clouds above the airplane. What are clouds made out of? Water. So airplanes, and in that last picture showed airplanes typically flying in that general, that's supposed to be an airplane. That's sad. Chad, don't laugh at me.
He is John.
So the airplanes typically go up above the clouds because the clouds equal weather, and you don't want to be flying in weather. You want to get above the weather. That's that graph. Let's try and answer these questions that are on page 4. Where's most of the where's most of the water vapor found? Troposphere. So again, this graph only goes up so far, and most of the water vapor is in the troposphere. Troposphere. Do not say tropopause. What happens to the atmospheric pressure, which by the way is just another way of saying pressure, as altitude increases? Okay, so we start off at 1 on the ground, and as you go higher, it gets closer to 0. So the pressure decreases. So in which sphere is there all the weather? Troposphere. Why?
Because that's where most of the water.
That's where the water is, and where there's water, there's weather. And finally, what happens to the temperature in each of the spheres as altitude increases? Troposphere, we go from -15 to -50, so that decreases. Just the stratosphere, what happens? Increases. Mesosphere, yep, we're back to decreasing. It's getting colder.
And the last one, I think that's degrees.
And the thermosphere increases, yep. And just to refresh your brain on how to use this chart that I mentioned at the beginning of class, it says average chemical composition of Earth's crust, hydrosphere, and troposphere. Write the composition of the troposphere in the table below. Refer to the ESRT page.
14.
One.
1.
So flip back to page 1. We want the composition of the troposphere. What is the troposphere made out of?
Potassium.
I don't think so.
Where do you see it?
Troposphere is right here,
Yeah, everything.
okay? Is it
21.1%.
21.0% what? Oxygen. So 21% oxygen,
78% nitrogen.
78% nitrogen, and 1% other. Now, notice they did not put anything in the rest of these boxes. What does that mean? There is none. They saved ink by not putting a 0.
We done?
So you do have 4 minutes to get started on your homework. I do think that'd be enough time to get a couple questions done. You have 16 questions for homework. I really need you guys to try, because by just circling answers, you won't get it, and we will not be covering this again this chapter. This is it for this reference table. So get your homework done and actually put in the effort.
Put in the work. Put in the hours.
Finally, remember, test corrections should be done by Monday afternoon.
Oh, we're just taking care of this.
Second period, I have a class, but you're welcome to come down and take the test in the hallway or in Mr. Miga's room or something. I think he has study